Yeah. I'm seeing, how do you know if it's recording is the question. All right, it is recording. Lovely, I'm seeing it. Good. We just came on there. Sangeeta, all right. Once you come on, and normally the mic comes on. All right, so yeah, back to here. Right, back to here. We're seeing the proof here, but where it comes from. Again, this is something I had. Just find it again. In the last handout I gave you a handout on gravitation, right? I'm referring to that handout, but I'll pull it up on my screen in a second. Right. Okay, so this is the handout on gravitation. You all have this, although I haven't taught this yet. But the basic point is where Newton's law of gravitation comes in. That is, when you have two masses, m1 and m2, these masses experiences a gravitational force that is given by this equation. Right? Now, that's the gravitational force. Also in class on Friday, I'd mentioned, for the people in Friday class, I'd mentioned that in order for a body to be moving in a circle, you need to have provided a centripetal force. Right? We just spoke about the centripetal force in the last session. So when a body is moving in a circle like satellites, in order for the satellite to have a stable orbit, that centripetal force we just mentioned, which is mv squared over r or mr omega squared, is provided exclusively by the gravitational force for moving satellites. So that's why I'm saying at the start of this question, it's right here, it's taken from right here in the handout. At the start of this question, I said that gmm over r squared will be equal to mv squared over r. For each of these orbiting satellites, gmm over r squared will be equal to mv squared over r. Well, when I make that equation, I can see from this equation the m's of the satellite will cancel out, right? And we end up with a simplified identity. I put it as a simplified identity because g and m, they are constants. If g and m are constants, we can see that from this cancellation, that v squared is inversely proportional to r. And I express that here, that v is inversely proportional to root r, which is the same thing. If I say v squared is inversely proportional to r, it's the same as saying v is inversely proportional to root of r. So that's where I started this proof right here. This equation, it's a useful identity to come to. It comes straight from here, right here. Now, if we are saying that the speed of orbital motion, that's what we're saying here, the speed at which a satellite has a stable orbit, v, is inversely proportional to the square root of the radius, then we have two situations here. We have one satellite, S1, and they're telling us that that satellite, S1, is orbiting with a radius of r. So therefore, for S1, V for S1, V1 as I call it, all right? I can write it again to kind of bring your mind to focus on it. I think I could write something like that. Yeah. What I'm saying is from here, V1, which is the speed of satellite 1, V1, should be proportional to 1 over the square root of r. Right? That's what it's saying here. And at the same time, for the second satellite, V2, that's the speed of that second satellite that's orbiting further away. Are you clear what's going on in this question? You have one satellite orbiting, S1 is orbiting at a radius r, and S2, the other satellite, is orbiting at a radius of 4r. Just on the textbook, are you understanding this? Or you want me to illustrate? I can illustrate it. Are you understanding this? What they're saying here? All right, I'll illustrate. Now, what I'm saying is, if you have, I'll change the color here to, I mean, we have a lot of our color thing. Where is it? Format, something like that. So we have a planet, right? That's our planet right there. Okay. And we have satellite S1. Satellite S1 is orbiting that planet. And satellite S1 is going right on the surface of the planet, a distance of R, let's see. That's satellite S1. Okay? For satellite S1, we can see from this identity here, from this equation here, for satellite S1, its speed is inversely proportional to its radius. All right? Sarah, you think you understand that? Shane, for S1 that is. Yes? Yeah? Okay, that's S1, right? Good, thank you. S2 on the other hand, the other satellite, and again, this is moving at what speed? The speed of orbit here is, I'm calling it V1, and the radius of that orbit, I'm calling it capital R. Good. Now, for the other satellite, that other satellite is orbiting at a further distance, a distance of 4R, orbiting the same planet. Ooh, that color looking bad. Undo. Too light. Something like brown. The other satellite, S2, is orbiting at a distance that is 4 times that. This distance here, this distance is 4R. And at the same time, this is moving at a totally different speed, V2. Good. So that's what's going on. Both satellites orbiting the same planet at the same time. All right? This planet has the same mass, and it has the same gravitational constant. So for V2, we can say V2 is proportional to 1 over the square root of 4R. Right? And that's what I kind of skipped past this stage here, and this illustration. I was going on in my head, I saw this, I saw that, and I just put them together. I just divided because the question wanted the orbital speed of S1. So we have to put V1 in the numerator. V1 is proportional to, right? And you just populate the equation. This is what you're going to get when you populate the equation. When you put in V1, R in the denominator, V2 for R in the numerator. It's just math after that. And you cancel out and you end up with V1 over V2 is root of 4, which is 2. And the answer therefore would be C. Okay, Sarah, Shane, Vishnu, whoever is listening, you okay with that, Tariq? Well, Tariq, you're not doing circular motion yet, so don't study this here. This is for the people who, again, who started circular motion, and they want clarity on this. I know Shane and so on, they started circular motion. It's good. Sarah, yes, good. All right, so let me just clear this drawing. Clear all. Right, it all works. That's number 10. Let's continue. Number 11. I was having fun here, as you can see. Which of this following statement best describes the motion of a geostationary satellite? And the first thing, it moves with the same velocity as it is. That's clearly not true. If the geostationary satellite moves with the same velocity, it will be left behind. What happens is, in a geostationary satellite situation, we have let's say a planet here, right? And this planet is in rotation. And this is where we're living on this planet. The satellite is being placed further out in space, like out here. And the important part about geostationary orbits is this satellite must remain, when the satellite moves through that horrible looking circle, the Earth would have completed 1 revolution. So clearly this satellite travels a bigger distance compared with the distance traveled with you on the surface of the Earth. So therefore the satellite could not be moving at the same speed. It has to be moving at a much larger speed. In fact, the velocity that is constant is called the angular velocity, that this satellite, starting here, will sweep out the same angle as you on Earth, which is 360 degrees. So to say it's moving at the same velocity is clearly rubbish. its geographical location changes as Earth's rotation. This is rubbish because it is counter to what geostationary is. Geostationary is that the satellite must remain directly above you all the time. Even though you're moving, the satellite is still above you. And to say the acceleration is zero is utter rubbish because clearly this thing is moving in a circle. The only way an object can move in a circle is if there's a centripetal force acting towards the center. So to say there is no acceleration is to say it is not moving in a circle, that's why I said utter rubbish. So the default answer is clearly the last one. Somebody. So the default answer is clearly the last one, right? So I'll clear this now. Clear all drawing. Okay, next question. The next question is on dimensions. And it's something we're all familiar with. The kilogram, the meter, the second are base units. Name two other base units. And the two others would be what? The Kelvin and what? Yeah, so well done, Shane and Vishnu. The next one will be the Kelvin and the ampere. Explain why the unit of energy is said to be derived. It's a derived unit because it's based on fundamental units, because energy is based on kilogram and meter and a few other things. All right, it's a derived because it's not one of these. This one here, I wrote up the solution. Now, determine the base units of density rho. Again, to determine any of the base units, you have to go back, as I said, to this equation. Could anybody tell me what an equation like this, the general name of this equation is called? Just type it in the box. What is the general name of it? That's right. Vishnu, you're on like boy today. Excuse the corny language. Okay, good. You'll get all that fun. Good. Density is mass over volume. Whenever you want to determine what the dimensions of something is, you always have to go back to the defining equation. Density is defined to be this. So we simply populate this equation and we get the dimensions of rho. Show that the base unit of pressure, again, we have to find the defining equation for pressure. Pressure is force over area, right? And because pressure is force over area, thank you, Shane. Somebody at least laughed at my corny joke. Pressure is force over area. Force has a defining equation as yet. The defining equation of force is mass by acceleration, and so we go until we end up with what the base units of pressure is. Right? They said, given that the constant gamma has no unit, determine the unit of C. So it's just a matter of us looking at the equation. Gamma has no dimensions, but we just worked out for P, we just worked out for rho. So it's a simple matter of populating this equation. That's what I did here. This power to the half is the square root sign. All right? So we really have no dimensions multiplied by the dimensions of P divided, and I did the division here by doing the reciprocal and multiplying, of course. So this is the division for rho. Rho is kilogram meter cube, then 1 over rho would be kilogram to the minus 1 and the m to the plus 3. And we solve and we end up with ms to the minus 1. That's what they asked, what is the unit of C? And they said, using your answer, suggest the quantity that C represents. And because the unit is meter per second, it can represent speed. So that is pretty straightforward. The next one is a nice little question on vectors. A car changes its velocity from 30 due east. So 30 due east would be like, 30 would be like, let's say this vector. That's 30 due east. And it's going to 25 due south. So it's going from 30 due east to 25 due south. So this is the final velocity. And of course, this is the initial velocity. There, so far. Now the first part, it does draw a vector diagram to show the initial and final velocities and the change in velocity. So this is the initial and final. how do we get the change in velocity? We had said before that the change in velocity is the final minus the initial. And we have v here. In order for us to add the initial, we have to turn it around. So this here is minus u. If that's u, this is minus u. So we really have to do an addition between this green and this orange vector. And I did it here. This is the, well, I suppose I inverted the colors here, but the 30, this is the minus u that we're adding to the v. And, you know, it just follows from there. The delta v is this. When you have this and that, you complete your parallelogram and your diagonal from where there are no arrowheads to where there are two arrowheads. That is the resultant. Oh, sorry, not the resultant. That is the change, right? Because you're trying to get the change here. Tell me, you got on that, everybody? Okay, I'm getting almost at it. Yep, good, thank you. The next part, calculate the change in speed. Now, speed is not a vector quantity. When we're talking about speed, speed is a scalar. So as far as we are concerned, the speed of this thing is just 30. And the speed of this is 25. So what is the change in speed? Is from 30 to 25. So you can call it 5 or minus 5 will be fine. Either call it the change is 5 or there's a decrease of 5. Right? There's no directional component because this thing is a scalar. And then calculate change in velocity. Right? Having drawn the vector diagram, you can simply use Pythagoras to find the diagonal because that is the hypotenuse of this right angle triangle, which is delta v. So delta v is 30 squared plus 25 squared. The root of that, that's delta v. And then we want to find the angle. So to find the angle, because they use north, south, east, and west, I'm going to try to express the answer from bearing. In bearing, this is north. That's north. So my answer would be all of this, right? All of that. But I know this straight part is 180. I know this part of that angle is 180. So all I really want to do is to use this triangle here to find theta. And we know that from this triangle, tan theta is really opposite over adjacent. Tan theta is 30 over 25. So this theta in here, this acute angle, is really 50.2 degrees. And can't you leave the normal angle? Which normal angle? Varun, Vishnu, which normal angle? On the diagram, I don't know what a normal angle is as against the one on the diagram, which angle? Oh, I mean, just put 50.2. That's what you mean, Vishnu, just put this as the answer? Well, no, I don't think so. I wouldn't accept that, you see. Why would I not accept that? Are you all seeing my argument? They reference their direction from east and due south, all right? They're referencing their direction from Cartesian, navigation. So I would prefer, although I'm expressing that answer here, I'm still going to go this far because I want to express my answer in terms of something that is similar. I could not get my answer in terms of east, west, north, and south, or northeast, or any of these other things. But I can use bearing, which is the closest thing to what they're using. All right? That's the way I would see it. That's the way I will expect it if I'm marking something. That's the way I will teach you to do it. You understand my logic? All right. So that's why I will work this out, but I wouldn't put this as my answer because, again, this is from some reference point. They didn't give me any reference. They gave me absolute references from Cartesian. So I'm giving them the same. All right? So you just have to add this 50.2 to the 180, and we will get our direction. All right? I'm going to clear now. Any questions? All right, everything clear. I'm going on to the next question now, which is, use this thing. Okay, this was so fuzzy, I couldn't really read this too well, you know. So I don't know. I really couldn't read this properly. The powers were all very fuzzy. So I don't know. I don't know how you're gonna I don't know how you're gonna deal with that, or if you have a cleaner copy of the question. I wasn't able to look for it or find it. So I'm going to skip that one. This one was rather interesting. This one was a really, really nice question. I tried to write up what the solution ought to be here for you. But I'll go through it with you now. This is a graph. Yeah, Sarah, you can WhatsApp it to the group. I can take a look at it. All right, so this one is probably the most challenging of all the questions on that paper. Well, I didn't look at the last one. I didn't get a chance, or did I? I tried to look at the last one, but we'll get to that. This one was a really, really interesting question. I was really happy to do this one. The graph, figure 4, shows the speed of 2 cars, A and B, while traveling along in the same direction over a period of time of 40 seconds. So here you have a car. I mean, think of you traveling down the highway, flying down the highway at, let's say, 40 meters per second. And at the same time, you overtake somebody who is really, really driving slowly. And when you pass them, they feel they want to catch up with you because you probably give them a slight or a bad drive or whatever. And as soon as you pass them and give them the bad drive, for example, they start accelerating. All right? That's what's pretty much going on here. They are accelerating, and then they stop accelerating and they're traveling at a constant speed while you continuing your merry way at 40 kilometers per or meter per second. And if you visualize that, when you overtake somebody, you would have gone past them, and the gap between you and the car would open up because you were clearly driving faster, right? They were traveling slower, you were traveling faster. You go whoosh, you go past them, and you open the gap between you and them. All right. So let's go along that direction. How far does A, this easy part, how far does A travel during the first 20 seconds? Well, the distance traveled by A, we know what kind of graph this is. This is a velocity time graph. And if it is such, then the distance traveled by A is simply the area of this rectangle. The area represents the distance traveled. So we can then find this area very easily. The area is 20 by 40, which is 800. That's, as I said, a straightforward part of that question. Next part, calculate the acceleration per car B. We know in a speed time graph, the slope do it a little bit faster. We know that the slope is equal to the acceleration. All right. So right here, right now, we have this as a sloping part here. We just have to find the slope. We just have to find the slope. The slope is the rise over the run, and the rise is from 25 to 50. So the numerator would be 25, V minus U. And the time, the run is 20. So 25 over 20 gives you 1.25. Pretty straightforward to get the acceleration. Right? How far does the car B travel during this time? Well, the other thing we know in graphs is that the area is equal to the, in this case, it's equal to the distance and not the displacement. Why? Because this is a speed. It's a speed time graph, not a velocity time. So the area under this graph will be a scalar distance. All right, so we simply have to find this, this area here, which is a trapezium. Sorry about the drawing. All right, to find the area of a trapezium, you have to have a half sum of parallel sides. So it's a half into 25 plus 50. A half into 25 plus 50 multiplied by the perpendicular distance between these, which is 20. So you have 750 meters. No problem. Calculate how far does B travel during this time. Right, the next part, what additional time will it take for car B to catch up with car A? Now, since they were together, remember at time t equals to 0, both cars were next to each other. One was traveling at 40 and one was traveling at 25. After 20 seconds, we have discovered that car B travels a distance of 750 meters. Very good. That's after 20 seconds. They continue to move, but after 20 seconds, we're freezing the motion for analysis. Car B would have traveled this much. But how far would car A have traveled? You didn't ask the question. But if you were to ask yourself that question, car A would travel this distance, this rectangle here. All right? Or they did ask the question. They did ask the question. We know that car A traveled 800 meters. So after 20 seconds, the two cars, they're separated by 50 meters. That's what I put. The difference in distance at 20 seconds is 50 meters. Car B is 50 meters behind the car A. So you have a situation where car B is here and car A is here. They're both heading that way. And the separation between them is saying is 50 meters. All right, so we got on that. Now, this is the trick part here. A is moving, B is moving, but the velocity of B relative to A the velocity of B relative to A is just 10 meters per second, because B is traveling at 50 while A is traveling at 40. All right? So as far as they are concerned, this could be considered to be stationary while this is traveling at 10. You all think you follow what I'm saying? That's a trick to the whole thing. That's one of the tricks in this question. That B is called relative velocity. We don't really teach it anymore, but it's a concept that is quite useful. The velocity of B relative to A is just 10. All right, so let me do it again. Yeah, A is traveling at 40. B is traveling at 50. So this gap is getting smaller. Why is it getting smaller? Because B is traveling faster. If at this point in time, A and B were traveling at the same 40 and 40, this 50-meter gap will remain forever. This 50-meter gap will remain 50 forever. But because B is traveling faster, the gap is closing. And because B is traveling 10 meters per second faster, this gap is closing by 10 meters every second. The gap is closing by 10 meters every second. Now, let me just go further with that. Let me show you that point, right? In 1 second, how far would A travel? Answer, in 1 second, A would travel 40 meters. in 1 second, how far would B travel? B would travel 50 meters. So it means that the space between A and B during that 1 second has decreased by 10 meters. That's the point. Are you seeing that? Kyra? All right? Okay, good. So the gap between B and A is closing by a rate of 10 meters every second. How far is the gap? The gap is 50 meters between them. So therefore, it will take 5 seconds for B to reach alongside A. It will take 5 seconds for B to get alongside A. And that is where I did the calculation, that the difference, all right, is 50 meters. And the rate at which the gap is closing is 10 meters every second because of the relative velocities. And therefore, the time it takes to close the gap will be the distance, which is 50 meters, divided by how much of that distance is being closed every second. And you get 5 seconds. All right? It takes 5 seconds to close the gap. Now, obviously, I mean, this is like, you know, if A would then speed up to become 50, then the gap will not be closing anymore. If A would move faster than 50, then the gap will actually open. You can play a set of games with it in your mind to see if you follow the concept. All right? A series of games you can just run through your head to see if you understand this concept. This gap is an interesting part of it. So what additional time will it take? It will take an additional 5 seconds. So what we're saying so far is at 25 seconds, the two cars will now be next to each other. That's what we're concluding right now. So I'm going to clear what I've written on the board so far. After 55 seconds, I'll write some new stuff. Like here, after, sorry, not 55, 25 seconds. Rubbish. After 25 seconds, then the area under this, that's what we're really trying to say. After 25 seconds, the area under this graph for B will be exactly equal to the area under this graph for A, meaning they're next to each other. They would have traveled the same distance from the time they first interacted. So now they're asking, how far would each car have traveled since t equal to 0? So you could have chosen this trapezium to work out the distance, or it's easier to use this rectangle, clearly, because this rectangle here, I'm saying, is equal exactly in area to this trapezium here. All right? So that's what I did. I did the easy part, which is I just worked out the distance traveled by A, and the distance traveled by A worked out to be 1,000 meters. B would have also traveled, obviously, 1,000 meters. The last part is, and the other part that really was fun to work, what is the maximum distance between them? And, let's clear the drawing. The maximum distance between them is in fact the area of this triangle here, I submit. Now think about it. All the while, A is traveling faster than B. So the gap is opening. The space between the two cars is opening. What happens at this time exactly? At this time, both A and B are traveling at the same speed. No longer is the gap opening. No longer is the distance between the two opening. If you have two vehicles on the highway, that's how you know if you're traveling faster than somebody on the highway. You're going down the highway and you see the gap between you and the vehicle closing. It means you're traveling faster than them, if you're behind them, that is. If you're behind a vehicle and the gap between you and them closing, it means you're traveling faster. If you're behind a vehicle and the gap is getting larger and larger, it means that they are traveling faster than you. Using the same analogy I just outlined. But if you're going down the highway and the distance between you and the car ahead of you is remaining constant, it means you're both traveling at the same speed. So if you wanted to know their speed, all you need to do is to look at the speedometer, because the space between you and them are remaining constant. Now, from here to here, the space between the two cars has grown. But once B starts traveling faster than A, this represents how much that area is going to be closing now, because B is now traveling faster than A. So the gap between the two, remember B is behind A. A is ahead, B is behind. All right? The gap between the two is closing. So to find the maximum distance from that argument has to be the area of this triangle here. Because once B starts traveling faster than A, that space between the two cars, they start getting smaller. Hoping I'm making myself clear. I don't know if I'm succeeding there. Do you all understand that this is the point where the distance is greatest between the two? Any further, I suppose I can explain it more, but all right, so people following. So far, I'm not hearing any dissenting voices. I have to go with I can't see you, so I have to go with the agreeing voice. So the task is to find the answer to this question. What is the maximum distance? Has to be to find this area. Now, this area is not immediately found. We can't just look at it and find it because we do not know this time. To find this area, we have to find this time, because to find the area of the triangle is a half base by height. However you want to do it, but you need these. You already have one dimension. You need this dimension. All right, but this dimension is interesting because this dimension here, this time from here to here, is the time it takes. It's the time it takes for B to go from 25 to 40. All right, and we know the acceleration. We know the acceleration of B is 1.25. So delta V, the change in velocity we are seeing, is equal to what? The change in velocity is from 40, is the difference between 40 and 25. The change in velocity is 15. That's a change in velocity. And acceleration we know is equal to what? It's delta V, is the change in velocity over the time taken. So to find the time, which is what we want to find at T is the time it takes for B to go from 25 to 40. So T would be equal to 15 over 1.25, which works out to be 12 seconds, which is what I already worked here. We good? So the time it takes to go from the time from here to here is 12 seconds, and it makes sense still because it's not more than 20. I mean, if we have gotten a value more than 20, we know we're doing rubbish, right? So the time is that 12 seconds right there, right? And once we get the time, you just use the area of the triangle story, and we get the maximum distance between them is 90 meters. And that's the answer to the question. Okay so far? Yep. All right, so that was a really nice question. All right, and then this one is I didn't get a look at it, but Sarah, did you all have trouble with number 16? I'm gonna check that dimension one. I know you sent me the image, so I'm gonna try to open it now. Right. All right, so if I'm going to try to, I'll give you a couple of minutes. The people who do circular motion, all right? I'll just give you all a couple of minutes to try this. The people who do circular motion and gravitation. I'm going to give you a couple of minutes to try this. At the same time, I want the rest of the group. I emailed, where is it? A file. Anybody from Tuesday class on here? Tuesday class, nobody. Oh, Marcus. Marcus, did Chiron and Marcus, yeah. Did I give you a handout with projectile motion questions? I'm talking about, I'll show you it. I think I emailed it today, but let me just show you what it is I'm talking about. Find it. Yes, this one here. Did I ever give you this handout in class? Or did you get this via email today? All right, good. This is another set of, this is all projectile motion questions. I've been writing solutions to these questions over the past few days. Sarah was she was working them, so she wanted some confirmation. The answer is a little bit off from the answers in this. Did you get this? The answers are in this as well. You should have gotten it. All right, but the answers are a little bit off because they're using G as 10, and we are forced to use G as 9.8. So the answers are a little bit off, but it's not by much. And what I've been doing is writing up solutions to these with some illustrations. So if you could try, if you don't do circular motion and gravitation, you could ignore this question for the next 10 minutes or so. I'm giving you 10 minutes to look at the question. You can probably try one of these questions here, all right? And I will show the solution to it as well. So we're breaking, I'm not breaking, I'm just holding on for 10 minutes while you all attempt the relevant questions. Circular motion people here. All right, so let's continue with this question first for the circular motion people. This is still debatable, as I said. Certainly not 3. 7 is still kind of close. So I think it will actually be more than 7. 4 the radius of the Earth is 6 by 10 to the 6. 4 by 10 to the 7 means it's really close to the surface. All right, so we'll just book it as 7 for now, but I'm certain it has to be, logically has to be more than that. Nobody's going to put a satellite that is less than 10 meters above the Earth's surface orbiting because it will smash into buildings or undulation of the terrain. So, right. So let's go explain what is meant by a geostationary orbit. A geostationary orbit, for the people who do gravitation and circular motion, a geostationary orbit is one in which the satellite remains at the same position relative to any point on the Earth's surface. Right, that's what a geostationary orbit. The satellite remains at the same point, the same position, relative to any point on the surface of the Earth. That's by definition. It's also in the gravitation handout that you got last day in class. that definition of what geostationary is. And when I get to that point, I'll go into more explanation. That's it in a short word. Calculate the angular velocity of the satellite. Well, they did tell us that. What is angular velocity? Angular velocity is angle swept out per unit time. Angular velocity, omega, is equal to the angle swept out divided by the time it takes to sweep out that angle. Now, when a satellite orbits the Earth, it makes one complete orbit. It moves in a complete circle. So the angle in radians that it covers is going to be 2 pi. That's what a circle is. 2 pi is the same as 360 degrees. And if it's a geostationary, the Earth takes 24 hours to complete a rotation. If the satellite is geostationary, it must have the same period of rotation as the Earth. In other words, it must orbit the center of the Earth in 24 hours. So that's why in the denominator, I convert 24 hours to seconds, 24 by 60 by 60. That's 24 hours. All right? And that, when you work it out, will give you omega. The speed of the satellite, V is equal to distance over that same time, 24 hours, this time from here. But what is the distance? The satellite, as I drew earlier, this is the Earth. And let's say the satellite is moving around the Earth. What distance does it cover? This is the Earth here again. What distance does this satellite cover in 24 hours? The distance it covers is the circumference of the circle, which is going to be 2 pi r, which we're not sure about, right? So we're going to use that. As I said, I think it's more like going to be 8 or 9, not 6 certainly, or 7, all right? So you could choose your value, but you choose your value for r, and that will give you, divide this, of course, by the 24 by 60 by 60. And that gives you the speed of the satellite. The acceleration, again, because we've just found the speed, it's just v squared over r, and r is whatever that is. Again, whatever you use for that. The force of attraction between the Earth and the satellite is a gravitational force, right? What is holding the satellite is a gravitational force. You have the mass of the satellite. Oh, you don't have the mass of the Earth. Well, again, there are two ways you can look. It's a gravitational force, but it's also, in this case, it's a centripetal force. That's how you have to look at it. And in fact, this, using the gravitational force, is how you would have found the mass of the Earth, because you equate the centripetal force to the gravitational force. So again, to find the force of attraction between the Earth and the satellite, we know Fc and Fg, gravitation and centripetal forces, are equal. So you could have used the centripetal force to find the attraction, and then use that attraction to find M. Let me see if I could. I've already piled up on the bottom here. Gravitation, yes. I showed this a little while ago, right? Where I said Fc, the centripetal force, is this, but the centripetal force is also a gravitational force. So because we already got V and the mass of the satellite and the radius, we could find the centripetal force, which is equal to the gravitational force. And then we can use that identity to solve for ME. All right, everybody? I mean, circular motion people, I mean. I don't want to stress the others. Hello? We clear? Got it? Awesome. All right, so let's clear this. There is a way, people, I mean, we're learning to use the software, right? But there is a way that you can also, like when I'm annotating or writing on this, there's a way that you could actually take control and draw on my screen that we're all looking at. And you can actually type on the screen. Who's doing that? How you do that? Ah, who's that? I don't know who did it. Who did it? Oh, Marcus, right. All right, so there's a way for you all to interact on the same screen. So this is like a shared space that we all can write on. We can write, we can clear. So that is a two-way kind of interaction. It's not just my voice. I'm just using a very limited way today because I am just answering questions and responding to feedback. But if you need to highlight something, you can actually use all of these tools on this surface, on this entire screen, so that we can have two-way interaction. Next part, explain why a GeoScript. Well, this is something I'll deal with later. I'm not going to answer this. It's a discussion question, and I don't think I can do this right now. I want, for the next 15 minutes, we have 15 minutes again, to look at that handout okay, Gyan, you said it's 10 to the 7. And we'll have to, it must be more than 10 to the 6. So 10 to the 7 means it's really close to the surface of the Earth, which might be a physical problem. But it doesn't matter. The point is we understand the concept. We understand the concept of this application. Thank you, Ganeshwari. Yeah, we're going on to that projectile motion handout now. Did everybody get this version of this document? Everybody got this version with this blue writing because on this calculation? That's a yes or no? All right, good. Yes, I think I just emailed that to everybody. I want now to go to the other document, which is the projectile motion. Spend 15 minutes on projectile motion, if you don't mind. That's not a child reach, I think. Hold on. I just have to open up for this chat. Just give me a couple minutes. Hello, Zidra. I'm going to open it now. Okay, I'm back. Yeah. Trying to find that handout, which is this one here. All right. So I am a strong believer in the philosophy that you need to invest time on the questions to really master the skill. So although I have solutions and I would write solutions and I would share solutions, you really have to use the solutions in a very a way that will help you. So this is the solution document, if you will. For this, I try to illustrate it so you will follow exactly what I'm doing. And I do detailed solutions, all right? These are all on, and I hope you follow them. It's an ongoing process. I just got up to, I don't know, question 9 or something, right? But detailed solutions are there for every single part of it with illustrations. All right, so I think the best thing for now is for me to email this to you, yeah? And you use it once you require it, once you want to do the projectile motion, you could just try the question and then, you know, go and check and see if you're right. If you get stuck, struggle through a little bit, go through the struggle. Struggle is important to really really grasp the thing. The struggle is important. So try to get it out on your own as much as possible. What I did was I did each question on a different, I suppose, page, but I mean, it's a continuous document, so you can. So far I'm up to question 9. I hope I have time to continue, but you know, sometimes time is a real challenging thing. So I'm going to forward this document to everybody in the group, and you understand it's paired with this that I've already sent. This document I've already sent, so you save it. In fact, I could put it in Dropbox, and from there, is that better? Put it in Dropbox, and that'll be good with you. Going once.